All right, let's continue from where we left off. So last time we were talking about these things called linear bounded automata, which are LBAs. So they're basically just a Turing machine, so it's just a normal Turing machine, where the tape is fixed to the length of the input. So we have these special markers or something, some kind of mechanism to tell us when we're at the ends because we can't shift the input around. Okay, so the question of whether A sub LBA is decidable was we showed that it was decidable. And the reason that it was decidable was that we can just simulate the machine, the LBA, for long enough, and we can detect whether or not it'll run forever. An LBA can always run forever, it could, but it's just that we can detect when it runs forever. Whereas with an arbitrary Turing machine, we can't. So then we wanted to look at the question E sub LBA, which is all the machines of the form M, where M is an LBA and L of M is empty. Okay? And we wanted to figure out whether this is decidable or not. So ECFG is decidable, and ETM is undecidable, and ELBA lives in the middle, so it could go either way. So we started to talk about these things called computation histories. And those are the configurations Z0, C1, C2, etc. And as long as C0 is the start one, and each configuration yields the next one in a transition, then we call this a computation history. So what could we do? So how would we be able to decide E sub LBA or show that it's undecidable? Well, if ELBA is undecidable, what we would maybe want to do is we can try to prove ATM is decidable using an ELBA decider. So, could we use computation histories to allow us to do that? So, if I just wrote computation C0, C1 right next to each other, it might not be possible to distinguish where the separation line between them is. So, yeah, because if I just wrote like Q0, W1, W2, and then W1, Q3, W2. So the split really is here, for example, but if I just wrote that 6-character string, I wouldn't be able to determine what really is the separator in between them. So what we could try to do is to write this computation history as one gigantic string with delimiters in between. So C0, C1, C2, and then up to Cm for some m. So could could an LBA figure out whether this is an accepting computation history or not? So if I tell you these configurations with pound signs separating them as delimiters, could an LBA figure out whether or not this is an accepting computation history? Well, suppose that we did get this on the tape, or something like it. Well, first off, what could cause it to fail? What could cause it to not be an accepting computation history? So the question we want to answer is how is the given string not an accepting computation history? So one possibility is that it contains 2 signs right in a row. Actually, that's not necessarily true, but actually, no, it is true because every configuration must have a state in them. So if it contains 2 signs in a row, then it obviously cannot be an accepting computation history because that means that something must have yielded to it or it yields something else, but it itself is not a valid configuration. So if it contains 2 signs, then it's not an accepting computation history. So an LBA really could just figure out whether it contains 2 signs because you can just scan through the tape and keep a counter for how many £signs you've seen, and when you've seen one, increase the counter, and then when you finally don't see one, set the counter back to 0. So it is possible to determine whether it contains 2 signs. Well, another thing that could cause it to fail is that C0 is not the start config. That's something that can cause it to fail. And remember that that's something of the form Q0, W1, W2 up to Wn. So if I tell you what the string W is and what the Turing machine is, well, this is predetermined. Once you know the machine and the input, those are determined. So then all we have to do is just embed into the LBA what the starting configuration actually is. And it could easily determine whether or not C0 is equal to this because it can just scan through and see if the characters match exactly. If they don't, then say it's not an accepting computation history. Well, then the other thing that can cause it to fail is that CI does not yield CI plus 1 for some I. So that means that we have something like this. We have CI here, and then CI plus 1, and then stuff after. But it does not yield the next one. So that means that there's a mismatch somewhere. And that's pretty easy to do because we can just look into the Turing machine's transition function to figure out, okay, well, what could the Turing machine have done? We can just see and just write out what the next configuration would actually be and see if CI plus 1 is equal to it. So it's easily determinable whether or not a given string is not an accepting computation history. So therefore, it is easy to determine whether a given string is an accepting computation history because if the computation... actually one more thing, I forgot. For an accepting computation history, it could be that the last one that we have is not accepting. And what would that mean? Well, that means that the state it has is not Q accept. And that's pretty easy to check. So if the state in there is not Q accept, then it's clearly not an accepting computation history. So then if the input string, which is C0, C1, up to CM, matches or passes all of these, then it must be an ACH. Okay, so why in the world are we actually even talking about this? So let's see. Well, let's talk about let's just say that the LBA here that we make here is B. Let's just call it B for this task. I'm going to create an LBA called B for this. So what is the language of B? And so remember that we're given M, the Turing machine M, and input W to that Turing machine. So here, well, what has to happen? Well, L of B is, well, actually the language of B is the set of all accepting computations histories of that machine M on W, because that's exactly what it does. So the B LBA here is accepting a string if and only if it's an accepting computation history. So it's the set of all ACHs of M on W. Well, what could happen? Well, since the Turing machine M is a deterministic machine, it can only have one computation on that input W. So it's either accepting or it's not. And every other possible string, because we're given the string here, every other possible input to this LBA must not be an accepting computation history, because there can be at most one. So there are actually two possibilities. Well, the language of B must be a single string, which is C0, C1, up to CM. So a single string in that language if M accepts W. But if M does not accept W, which is in this case, if M does not accept W, so if it doesn't accept W, there is no ACH that in existence. So B could never accept in that possibility. So then that language is empty. And now we finally see why we're talking about this. So the language is either not empty or empty, depending on whether or not M accepts W. So how do we decide ATM? So to decide ATM, using a decider for the emptiness problem for LBAs. So on input, let's see, MW, where M is a Turing machine. So M's the Turing machine, and W a string. So then let's form the LBA B as before. And we have to note here that this is based on M and W. So the LBA is actually going to be different for each machine and each input, because it has to have the start configuration right, and the transition function is embedded into the LBA here. But once I know the Turing machine and the input, then I can make the LBA. There isn't a universal LBA here. It depends on each machine and input. So then let's run the supposed decider for the emptiness problem for LBAs on input B, the LBA we just made. So it's a decider, so if it accepts, then what does that mean? That says that B has empty language. Well, in the construction of this machine, well, if it had empty language, then that means that M does not accept W. So then for our ATM problem, we need to say reject here. So in this particular case, we have to do the opposite. And then otherwise, then that means that the ELBA decider says no, the language of B is not empty. Well, the only possibility is that M accepts W, because that's how we made the machine in the first place. So that means we need to accept here, because we've determined that M does in fact accept W. So that's actually a proof then that the emptiness problem for LBAs is undecidable. And so that kind of completes the collection of the emptiness problems. So EDFA is decidable, ECFG is decidable, ELBA is undecidable, and ETM is, of course, undecidable. We've already seen that. Cool. So let's try to see where we are right now. So, and actually for this particular problem, for emptiness of LBAs, you'll be proving it is undecidable in a different way on your homework 9. So let's figure out where we are right now. So we have basically 4 models of computation: DFAs and NFAs, even though they're the same. Then CFGs and PDAs, even though they're the same. We have LBAs now, and we have Turing machines. And for the types of problems, we have the acceptance problem for DFAs, CFGs, and whatnot, the emptiness problem for these, the EQ problem, the equivalence problem, and the all problem, determining whether the model actually has language equal to sigma star. So the acceptance problem was, so I'm going to have a check here meaning decidable, and X to be undecidable. I won't deal with whether it's recognizable or not. But the A DFA, that was clearly decidable. A CFG was decidable. A LBA was decidable too. A TM was undecidable. And in fact, for Turing machines, the answer is no for all of them. That's pretty clear. The emptiness problems was decidable for DFAs all the way down. And in fact, we've seen that. CFGs, we showed that E CFG is decidable. And we just showed that E LBA is undecidable. In fact, the E LBA undecidable proof shows that EQ LBA is also undecidable too. And actually for all, you can actually show that that is undecidable for LBAs also, using a very similar proof technique to what we just did. So the question is now, we have 2 boxes left. So it's for CFGs. What do we put here? And you can actually kind of see, well, if it was to the left of a check mark, then it will also be a check mark. And if it's to the right of a X, then it will also be an X. But it's between a check and an X, so we can't actually determine anything from here. So let's actually talk about, and I think in a homework or a quiz or something, you were asked about all CFG and EQ CFG, and you showed that if all CFG, if EQ CFG were decidable, then all CFG would be decidable. Because then you can just test equivalence with sigma star. But what we're going to look at here is the all CFG problem. So let's recall what that is. That's all the grammars G, and the language of G is sigma star. So let's see. So could we use the same idea for the LBAs here? Well, here's the problem. So let's just say that we wanted to use the same proof technique that we had before. So if we had C0, C1, C2, etc., up to Cm, and could CFG determine if this is an ACH? So we saw we could do it with an LBA. Could we do it with a CFG? And it turns out, no, we actually can't. So why can't we? That doesn't prove that it's undecidable or anything, but it's just that this particular representation of a computation history is not the one to actually work here. So why not? So let's look at this language. So WW, where W is in 0, 1 star. So you can actually prove that L is not a context-free language. And the string that you pick here, is 0 to the p, 1 to the p, 0 to the p, 1 to the p. And you can actually show that you will always leave L here. So why do I bring that up? Because if you visualize two adjacent configurations, say like these two, then think about what they're doing. So the vast majority of the tape in these two configurations are going to be identical other than a few small positions. So it has a really sound resemblance to the L language here, because if we had like a really, really long string at the very beginning, so like W1, W2, W3, up to Wn, well then what the Turing machine would do is the only thing that will change are these two places, right? Because the machine will move right and change the symbol. Let's just say maybe it'll be A, Q3, but then the rest of the tape is exactly the same because it only moved one position. So you can actually get a pumping lemma style proof based off of these that will allow you to generate a string that is not a computation history at all. Because what you would do is you would pump in a particular part and not in the other part over here, which would violate the condition that one configuration yields the other one. So is there any way that we can repair this? So what we could do is look at this other language, which is WW, but we're going to reverse one of the two W's here and still in 0, 1 star. Well, this is, so L prime is a CFL, and we've actually seen this before, because you can just have something like, oh, I don't know, 0S0 or 1S1 or empty. So something like that. So it is a context-free language, because it's the set of all palindromes. So what we could do here is let's represent the computation history in a slightly different way. Let's represent it like this. So C0 first. It doesn't really matter what C0 is, but C1 is going to be in the reverse order that it normally would be. Then C2 is back in the right order. Then C3 is in the reverse order, and etc. up to CM, and maybe let's say that one's also reversed. So what is this called? This is a reversed accepting computation history, because half of the configurations here are reversed. And this allows us to do this because it has a sound resemblance to L prime, because in most of the positions, they are going to be almost identical. And if we actually visualize this, so let's bring down the two two configurations that we had before, so Q0, W1, W2, up to Wn. Well, for the next one, it's going to be in the reverse order. So that's Wn, Wn minus 1, up down to W2, which will never change, at least here. Then let's say we had Q3 and A, just like before. So this middle part right here is identical across the pound sign. So we could actually, for two given configurations, make a grammar that generates strings like this. So let's see. Well, what could we do here? Well, the problem is when we have this third configuration. So actually, I'll just put it right here. So let's just say I have a B, Q5, W3, up to Wn. So this one is normal in the right order. This one is reversed. This one's back to the normal order. So if you think about what a PDA, for example, would do, then what it would do is it would push on the first part or something like it, and then pop off the second part. Well, then how does it go back through the input and take this second configuration right here and start working in testing whether it follows for the third configuration here? I'm not saying that that's the only way it can be done, but it would have a bit of trouble no matter what strategy you pick if we have enough configurations. So let's try to proceed in a way that we had before, but try to achieve the opposite goal. So if we're given a Turing machine M and input W, can a CFG or whatever, or PDA, recognize all strings that are not reversed ACHs? So let's try to let's proceed as before. So what could go wrong? Well, the string contains two pound symbols. Well, how can we represent this? Well, if it contains two pound symbols, the way we can represent it is anything can appear before the 2 pound symbols, then the 2 pound symbols, and then anything after it. And this is a regex, which is clearly context-free. And then here, let's see. So the second thing that can go wrong is C0 is not a valid start config, which means that any string at the beginning, any string at the beginning cannot be Q0, then W1 through WN. So, well, what is the starting config? So that is Q0. Actually, I should fix this right here. It's not sigma star because that's the input alphabet. The right thing here is gamma because that is the tape alphabet. So let's just remind ourselves that that's the tape alphabet. So what are the possible things that could appear? Well, the right way to start it off is # Q0, W1, W2 up to WN. That's the right way to start. And then #, then sigma, oops, not, I did it again. It should be gamma star. That can be anything after. Well, then I want everything else that could possibly happen. So that is, I want the complement of this. So if you have anything else, then that means that you didn't have the start configuration. Well, let's see. The stuff on the inside, that is, actually no, it should be this way. But it doesn't change it. So the stuff on the inside, that is regular because it's a regular expression, and complementing it is regular, so this is regular. It's not a regex, but it is regular because regular languages are closing to complement, as we all know. Cool. Well, let's see. Well, what else can go wrong? Well, CM is not accepting. Well, what could happen there? Well, let's see. Well, then that means that a whole bunch of stuff came before, then #. And then, well, let's see. Well, what are the W's here? So the W's are part of the tape alphabet. Actually, I should also amend this further. Yeah. So remember that the states are also appearing. So the gamma here really should be gamma union the set of states, because the sets of states are part of the input as or in this string as also. So it's not just tape characters. And same thing right here. So gamma union states. So then that means here anything can appear before. Oops, making errors. So for the accepting part, so anything could appear before, and then right at the very end, so this is why I had the Q included. So I want a bunch of I want a bunch of tape characters to appear here. And then right here, I want Q take away Q accept. So whatever the state is, it's not Q accept, and then anything after it with a pound sign. And this is also regular because it's a gigantic regular expression. Another thing that can go wrong, a lot of things can go wrong here, is at least two states in a single config. Although this will actually be handled by the next one, but I might as well just do it anyway. So then that means that we have a bunch of stuff that can appear before this particular config that has at least two states in it. Then pound sign, gamma star, something of Q, anything, any tape characters, then any state, so two states here, and then anything afterward. Actually, it really should be gamma union Q star, although the details aren't really that important. Yeah, so the details aren't really important here. It's just saying that we are allowing ourselves to have anything appear before or after. Actually, I should even amend this further. So the pound sign should also be included in the stars. You see how this is actually not that important for details? It's just saying that we can make a regular expression or something regular from it. So then the only thing that can possibly go wrong is CI does not yield CI plus 1 for some I. And this is where the CFG really shines. Because, well, to get something like CI and then CI plus 1 reversed afterward, with stuff appearing before or after, well, we need a CFG to do this. But the thing is, we need it to happen for some I. So this is the fact that CFGs are non-deterministic that allows us to get this. So it could non-deterministically guess which CI is causing the issue. And if it's destined to accept, it will find it, or find one that has that property. So the thing is, well, let's see. Well, what are these configurations looking like? So they have a bunch of stuff, and let's say that if they're not if CI plus 1 is not yielded from CI, then that means that they differ in at least one position that actually matters. Well, they may differ. It could yield CI plus 1, but still differ because of the transition that occurs. So it differs in a position that actually matters. So let's see. So let's just say that this is the position that matters. Well, then let's just say we have something like this. So right here is the differing position. So what could go wrong? Well, it could be that the transition occurs here or here, but since we know the Turing machine, we can just embed all the possible things that could happen there into the grammar itself. And if it happened over here, for example, on the opposite ends, we can again do the same. But suppose that we're in this case. Well, then this part right here must be exactly the same, although reversed, on both sides of the pound sign. And we could generate all the things that could possibly happen as long as we have the same string before and after. That's the WW reverse type language. It's not exactly the same, but it's really close. So I claim that this is a CFL. So if we look at all the possible things that can go wrong, well, we have something that's regular, or something that's regular, or regular, or regular, or context free. So the union of all of these is a CFL. So why do we want to care about the strings that are not accepting computation histories? Well, if there's no accepting computation, well, actually, let's write this out. So M on W. So what could happen? So it could either accept W or M does not accept W. Those are the two possibilities that could occur. So what could happen? Well, if M accepts W, then that means there is an accepting computation history on input W. So that means that there is some string that this grammar or whatever does not generate, because the string it does not generate is the accepting computation history. So that means that this language of this context-free grammar or whatever we made is not sigma star. But if M does not accept W, then there is no string that this grammar does not make, which means that this language is sigma star. So to decide ATM, what could we do? It's very simple. So on input MW, where M accepts W, well, I went off the rails there. If I can determine that, then I don't need this whole nonsense anyway. So where M is a Turing machine and W a string. So then we are going to build a CFG called G as above. And of course, just like the LBA situation, we're going to use the Turing machine and the input to make this grammar, because the behavior of this grammar heavily depends on the machine and the input W. So then run supposed decider for all CFG on the input G, the grammar we just made. So then if it accepts, so if it says yes, then that means that the grammar we just made accepts everything, it generates everything, which means we're in this case right here, which means M does not accept W. So we need to reject. So it's very similar to before, and then otherwise accept for nearly the same reason. So I'm gonna stop there. So those are two problems that we can show to be undecidable. So we finally can complete the picture here. You can actually prove that EQ CFG is undecidable, because if it were decidable, then you could decide all CFG by testing equivalence with sigma star, but we know that's not possible. So the answer is no for these. So we can finally complete the picture in some sense on all of the models that we talked about. So the A problem is decidable on 3 of them, the emptiness on 2, EQ and all are decidable only on 1 of them. So I'll see you next time.